In this video, we will be looking at the derivative of a vector function. So let's say that we have a curve C that is parameterized by the vector function out of t with components x of t and y of t. And we want to define the derivative of this vector function. Now, to have some context in mind, let's say that C is the path of a moving bug, and out of t is the position function of the bug. So what we want to know is how to define the derivative of out of t. Now, we define the derivative of out of t by the following limit. So r prime of t denotes the derivative of out of t, and it is defined to be the limit of the ratio out of t plus h minus out of t over h as h goes to 0. Now, we also use the notation dr dt in place of r prime of t. Now let's see what is this limit in our picture here. So out of t is the position of the bug at time t, and then out of t plus h is the position vector at time t plus h. So then notice what is out of t plus h minus out of t. Out of t plus h minus out of t would be the green vector minus the vector in black. So this difference is the vector that starts at the vector from the tip of out of t to the tip of out of t plus h, right? That's the out of t plus h minus out of t. And if I divide that by h, I still get, h is a scalar, so I still get a vector that's parallel to the blue vector. So notice that out of t plus h minus out of t divided by h would be a vector that is parallel to the blue vector, and then as h goes to 0, this vector is going to move. So this point right here is going to go toward the point. So the tip of out of t plus h is going to approach the tip of out of t as h goes to 0, and as a result, the vector out of t plus h minus out of t divided by h is going to move, and it's going to approach the tangent. It's going to approach to a tangent vector to the curve at the tip of out of t. Okay, so and the derivative in the context of the bug, the derivative of out of t would be the velocity of the bug, because this limit is basically in the numerator we have the change in position divided by the change in time. So this is the rate of change of position with respect to time, and so this derivative gives us the velocity of the bug. Now, what is this limit? Well, let's write down what is out of t plus h. Well, out of t plus h would be the vector x of t plus h comma y of t plus h, because recall that those are the components of r. And then minus out of t is, of course, x of t comma y of t. And then when we subtract these vectors, we subtract component wise, so we get x of t plus h minus x of t comma y of t plus h minus y of t. Now that's the same as x of t plus h minus x of t over h comma y of t plus h minus y of t over h. So we are basically then taking the limit of this fraction and the limit of this fraction, but the limit of this fraction is exactly the derivative of the scalar function x at t, and the limit of this fraction is the derivative of y at t. So we see what we have found then is that r prime of t is equal to x prime of t comma y prime of t, or in the notation of the differentials, this is dx dt comma dy dt. And if we are thinking of r of t as the position vector, then r prime of t, it would be velocity, which we denote by v of t here. Now, so what we have found is that the derivative of a vector function is the same as so you take the derivative of a vector function by taking the derivative of its components. Another thing that I want to mention is that in my discussion here, I took a curve in the two space, but our discussion applies to curves in any other dimension, in particular to curves in the three space. One more. So if this is the velocity vector, then what is the speed? Well, speed is a scalar. So speed nu of t is basically the length of the velocity vector. It is the length of r prime of t. So since this is the velocity vector, the length of that would be the root of dx dt squared plus dy dt squared. And also the acceleration at time t would be the derivative of velocity, or the second derivative of the position vector r of t. So this is the r double prime of t. That's the acceleration. Okay, so the derivative of a vector function r of t in the three space is r prime of t, or dr dt, where dr dt is the vector with components x prime of t, y prime of t, z prime of t. In the alternative notation, it is dx dt, dy dt, comma dz dt. So this is when I have a vector function in the three space. Okay, so let me recap what we have just said. We said that if I have a parametrized curve which is parametrized by a vector function r of t, then r prime of t is going to be tangent to the curve at the tip of r of t, and the length of r prime of t is speed. The second derivative of r of t is the acceleration. Here I want to introduce another quantity, which is t of t. T of t, it is defined to be r prime of t divided by the length of r prime of t, and this is the unit tangent vector in the direction. It is the unit tangent vector that is parallel to r prime of t. So it is if I think of r prime of t as the velocity vector, then we are saying that the velocity vector is tangent to the path, and t of t is a unit vector in the direction of the velocity vector. So again, the velocity is tangent to the path, is what we are suggesting here then. Okay, so let's now do an example. Let's say I have a curve that is parameterized by the vector function r of t with components cosine t, sine t, and t, and I want to find its derivative, and I also want to find the equation of the tangent line to the curve at the point where t is 0. Okay, so how do I do it? Well, r prime of t is going to be derivative. So how do I find r prime of t? Well, I take the derivatives of the components here. So derivative of cosine t is negative sine t, derivative of sine t is cosine t, derivative of t is 1. And so first of all, since I want to find the equation of the tangent line at the point where t is 0, let's compute that point. So when t is 0, what point am I getting? Well, what is out of 0? Out of 0 is cosine 0, sine 0, and 0. So cosine 0 is 1, sine 0 is 0. So let P be the point out of 0, which is 1, 0, 0. And that's the point associated with the t value 0. Now, what is r prime of 0? R prime of 0 would be well, 0, sine of 0 here, cosine 0, so we get 0, 1, and 1 to be the value of r prime at 0. So r prime of 0 we know is a vector that is tangent to the curve at the point at the tip of at the point out of 0. So then r prime of 0 is a vector parallel to the tangent line at the point P. So its equation would be x is equal to p plus t times v. So capital X is xyz, p is 1, 0, 0, and the v is v of 0, which is 0, 1, 1. So x is 1, y is t, and z is t. So that's the equation of the tangent line to the curve C at the point where t is 0. Okay, so with this example, I want to stop this video, and if you have any questions, go ahead and send me emails on it. So again, the key statements that I made here is that the derivative of a vector function is the same as the so when we are taking the derivative of a vector function, we take the derivative component wise, so we take the derivatives of the components, and the derivative is tangent to the path, and we have this unit tangent vector that's r prime of t over the length of r prime of t, and we did this example. Okay, so let's stop here, and I will see you in the next video.